Welcome back to pipe B to D. So going into B, we have an area, a time of concentration, and a runoff coefficient. So we're going to use Q equals CIA to figure out how much water goes in there. So Q is equal to CIA. The intensity is 120 over T plus 20. We're given a time of 15 minutes. So that's going to be 120 divided by 35. 3.43 inches per hour. So Q would be equal to 0.4 times 3.43 inches per hour times the area, 40,000 square feet. Don't forget your acre conversion. And I should mention, you could also convert your inches per hour into feet per second, and then you could use the square feet, but that's just a miserable calculation to go through. Keep it simple. Q is equal to 1.26 CFS. Let me just check that because that sounds kind of small, but it's possible. All right, 40,000 divide 43560 times 0.4 times 3.43. Yep, 1.26 CFS. Okay. So now we have, going into this, .26. So going into this pipe, we'll call it Q total. That's going to be a total of 6.14 plus 1.26 plus 6.77. Now we're talking about some serious water. 6.14 plus 1.26 plus 6.77, 14.17. Perfect. I love it. Now we're going to see some water flow, theoretically, because it's not really ever going to get that much. But I get to choose pipe sizes that are not just 15 and 18-inch diameter pipes. Engineers get excited about stupid stuff, and this is one of those things. Small pipes are not that exciting to work with. But when you get up to the larger ones, 18, 24, you get to design or build a 48 or a 60-inch pipe. Best day ever. Okay. So let's now see what we have with that. On this one, all I'm going to tell you is I want the slope to be 1%. I want you to choose a diameter and a velocity. So keep the slope at 1%. There's your CFS you have to maintain. See what you come up with. So pause it here, give it a shot, and we'll talk about what your design was afterwards. Okay, welcome back. So let's see, 14.16 is about there. A slope of 1%. Sorry, my fingers grab too much of the screen when I try and move it around. I'm hoping I'm not getting you too seasick watching this. 1%, 1 divided by 100 is 0.01. So that's going to fall over here. So I need to have a line that falls between those. Looks pretty good. Okay. So the first thing I always want to check is my velocity, because if I'm over 8 feet per second, I got to go something different, because that's going to be a big problem. 8 feet per second with the water, what actually happens to the pipe, just so you know the reason why we don't want to use that, is the sand and grit that gets carried by the water will actually scour out the bottom of the pipe and cut it open, especially with the plastic pipes. The concrete takes a few years to get cut through, but the plastic pipes, it acts like a water jet, And if you have fast moving sandy water, which happens in the springtime when you get these big rains after a lot of sand and salt goes down from the wintertime, it tears the pipes to pieces. So, keeping that water at that 4 or 5 foot per second is much better than going too high. All right, so anyway, we don't have a perfect solution here. So 18 inch or 21 inch, which is better to go with? Well, let's look at our options here. If I go with let's go with the 18 inch, and I go with a slope of 0.1, my velocity, that looks great. So I'm still in that neighborhood of being between 2 and 8 feet per second, actually right around 6 feet per second. So then I go over and check my Q, and I realize, well, my Q, it can only handle about 11, 10 and a half, 11 cubic feet per second. I need to handle about 14 cubic feet per second. It's only able to handle 10. That pipe's not going to work. Now, some of you are probably thinking, yeah, but it's pretend water anyway. You rounded up pipe AB and you rounded up pipe CB, and now we have all this extra rounding. We have plenty of capacity in there. Yes, but once you start doing it one way, you got to carry it through the entire way. Otherwise, let's go ahead 30 years from now. There's a flood. Someone says, let's go check the design, and they see how you rounded up for the first two pipes, but then created a bottleneck later on. You're going to have some liability in that. So once you start designing it a certain way, carry it through the entire way. And again, we're talking about, first of all, it's not your money, so don't worry about it. No, that's a bad attitude. It's not a huge increase in cost to the developer. So you're not talking about, we're talking about maybe $1,000, $2,000. We're not talking about tens of thousands of dollars. And you should always design like it is your money. All right, so let's see, keep slope at 1%. I shouldn't put those dots on there, they're too big. I won't do that again. And 21. I think we're good there. Okay, so when I'm looking at this, it looks like my velocity is about 6.6 feet per second, slope of 0.01, diameter of 21, and a Q of 11, 12, 13, 14, 15, 15 and a half. It's between 15 and 16. I can't see it too well, but I think it's in there. That's a design. I could hand that into the town and be good with it. Unfortunately for you, I'm not the town. I'm not good with just the nomograph. I want to see calculations. So, on our calculations, we know that diameter is 21 inches. My slope is 0.01. We want to find velocity and Q. So, pause it again, do these calculations, and then we'll come back and do it, and you can watch me do it. Welcome back. And I'm sure some of you aren't pausing it, so it's kind of an awkward silence for both of us. Let's see. 1.486, R to the 2/3, S to the 1/2 over N. I've never spoken to myself so much as I had in the past 5 weeks now, 4 weeks. Let's see, 21 inches. Let's see, that's 21 divided by 12. 1.75 over 4 to the 2/3, and 0.01 to the 1/2 over 0.013. .75 divided by 4 raised to the 2/3. I feel like I messed that up. Let's do it again. 1.75 divided by 4 equals, raise that to the 2/3 times the square root of 0.01 times 1.486 divide 0.013. 6.6. I think that's where we were, 6.58. Yeah, 6.6, good. Okay, I'm going to take that number. Q is equal to AV. Well, that's horrible. Q, that's even worse. Q is equal to AV. So Q is equal to 21. 21 divided by 12, a 1.75 squared pi over 4 times 6.58 feet per second. So Q should be around 15.5 when we're done. And that's what's nice about this nomograph. It tells me if I'm doing my math wrong. Times 6.58, 15.82. Okay, so that's what that pipe is capable of handling. And that's actually what we'd like to see. It had to handle 14.7. We're going to actually make it handle 15 point, oh, where was it? 15.82. So we like it when those numbers are close together. So when the 15.82, which is what it theoretically can handle, is very close to what is actually going into it, that means you have a well-matched system. You're not creating a lot of wasted capacity in here. Now, before we move on, let's see what would happen if we went back to what this originally had to handle. Originally, if we go back in time, this Q was 5, and this Q was, I think it was like 4.87. I erased that. Let's see. So if that was 5 and this was 4.87, that Q would have been 5 plus 1.26 plus 4.87, 5 plus 1.26 plus 5 plus 1.26 plus 4.87. That would have been 11.13 CFS. So from what actually could be flowing in the pipe today, 11.1, we have it up to about almost 16, so about 5 cubic feet per second more than is actually could actually flow through it today based on today's design. Just to show you one other option, what else could happen, you could pipe in another catch basin at some point in the future with another 5 CFS. You could sell those rights to a neighboring developer. So this way they don't have to build their own recharge basin. Hey, you can use ours and we'll share the pipes. Well, the town could make that offer. Lots of things we can do with that water. Okay, 15.82. So let me pause this here and then we'll move over to pipe DE.